when people were building the LHC, which is a big particle physics experiment, there was someone who wrote a paper that said, well, when you turn this thing on and you collide these particles, they're going to turn into a black hole. There's a chance that they're going to turn into a black hole. And so committees were formed. And people had to think about this carefully and write a reasoned response.
Welcome to the UIUC Talkshow. Our goal with the show is to introduce you to the most interesting people with the most interesting ideas. Today we are having a conversation with Dr. Gammie. Welcome.
Thank you. It's nice to be here.
I have a question for you. It might sound a little overwhelming, but I'm very curious. So I was thinking I want to model an accretion disk. So how do I go about doing that?
Okay, that is kind of overwhelming because that's what I spent a good part of my career doing. So I should say first what an accretion disk is. Yeah, sure. So most people are familiar with Saturn's rings, which are kind of like an accretion disk where solid particles of ice settle down into a narrow ring orbiting the planet. And the same thing can happen with gas around any central body. So it's believed that this happened in the early days of the solar system, where gas fell in and some of it collapsed to form the sun, and some of it orbited the sun, and then that material that it was orbiting the sun, which is known as a circumstellar disk or a protoplanetary disk, had dust condensing in it, little rocks condensing in it, and it eventually gathered together to make the planets and the asteroids and the comets. And accretion disks are found all over the place in astrophysics. They're found around black holes. Wherever you have a central body and some, gook around it, it tends to form an accretion disk. And the way we do this is through using every tool available to model accretion disks. So I think there's a lot of opportunity now in using big computers. So there's really large exascale machines coming online. There's a machine called Summit at the Oak Ridge National Laboratory that we run models of accretion disks on. And there are even bigger machines coming online just now. So there's going to be a big one come online at Argonne in the near future, and another big one called Frontier at Oak Ridge that's kind of online right now. So I think the simple answer to your question is that we write a computer code that models the stuff in the disk, and then we write a proposal for computer time, and then we get the computer time, and then my graduate students go out and run the code on the machine, and then we try and figure out what it all means.
How did you start? Like, let's say you're starting with anyone new, they're starting with a blank slate, right? Let's say you've never run a computer simulation before. You might have some knowledge of what an accretion disk is, but you don't know how to start to even begin coding to model it.
Yeah.
How do you deal with that thought process of coming up with?
Yeah, so that is why students who are interested in this find faculty members to work with to sort of lead them along the way, to have kind of an apprenticeship in the field. And usually the way this comes about is some graduate student arrives. They thought they were interested in condensed matter physics or something, or particle physics. And we wind up talking, and they say, well, maybe astrophysics is interesting. And I say, well, come to my group meeting. We'll have a little problem you can take a look at. And then gradually, they begin to figure out what's going on. And for my graduate students, usually by the end, they're involved in some big collaborations outside, and they're setting up their own new projects and everything. So there's some kind of transition that occurs where people work through that thought process you were talking about, and that happens over the course of their PhD. So I got to this in a very roundabout route because I went to college thinking I wanted to be a lawyer, and but I started out as a math major wanting to be a lawyer, and I went in to talk to my advisor, who's
Is there any specific reason why you did math? If you knew you wanted to become a lawyer, just curious.
I just liked math.
Okay.
Yeah, and I knew that you can go into law or actually many other fields from mathematics. Yeah. So I went into my advisor's office. I didn't know this, but he was a really famous mathematician, and I said, look, I'm going to be a math major, but I want to be a lawyer. What should I study? What courses should I take? What do you advise? And he said, I think you should take a course in statistics. That's very important in the law. And I thought, at that point in my life, I thought there's nothing more boring in life than statistics. And I absolutely do not want to do that. And so I started rethinking what it is I was going to do. And then I met my wife, and she was settled on going to graduate school, even as very early in her undergraduate career. And this was just a completely foreign concept to me. Like, no one in my family had a PhD. And so I started asking around about that, and I found out I could go to astronomy graduate school because it turned out I had enough in physics and enough in math to do that. And so I did it, and things were successful. I think that nowadays it doesn't really work that way for people in your generation. People feel like they have to get into the career almost as soon as they get to college. They want to start, they want to start getting research done so they can get into graduate schools and so on. So I don't think my path into the field would work nowadays, but it did give me a nice chance to sort of explore a lot of different ideas, a lot of different courses, and sort of move toward understanding things that would help me in modeling accretion disks.
What inspired you to come to astrophysics? Because you entered college thinking of doing becoming a lawyer, right? And then you take a turn to sciences. So how did that transition begin, or how did you come to realize that no, I actually might want to do a PhD in astrophysics?
Yeah, as I say, it was a pretty slow thing. So I started taking courses in physics, and I really liked them. I took an introductory physics course. It was at a very high level. So everybody in that class basically became a physics professor. Peter Schiffer, who's a professor of physics here for a while, was in that class. He was the vice chancellor for research, and everybody else became a professional physicist. So we were all working on our problem sets together and thinking about physics. So that got me interested. It was an interesting group, interacting with people. Oh, we can do it this way. No, we can do it. It was great. It was very interactive. And then I think the next big step was taking a course in general relativity.
Right.
And I took a course in that from Lee Smolin, who's now a fairly well-known popularizer of physics, in addition to being quite a distinguished researcher at the Perimeter Institute in Canada. And he was just interesting, and it sort of suited my sense for mathematics. And then I got introduced to another professor who worked on black holes. And so I learned a lot about that. And then I applied to graduate schools. And it must have been a lull in the applications, because somehow I got in and things worked out. Yeah, so slow process.
Right.
Yeah.
Yeah, that's a pattern that we've realized is that a lot of you guys, meaning the professors, a lot of you guys, you guys were interested in one thing, but you guys are not really worrying about, oh, I need to get a grad school at this age with this amount of money, and then I want to do research with this X professor. So like everything is so planned out that causes so much anxiety and pressure for people today that they don't have time to even just think and just think
Yeah.
about nothing.
Yeah.
Which is something I find interesting because you guys seem to have made it, whatever that means.
Whatever that means. Yeah.
And you guys were just more relaxed about things.
Yeah. Times change. I have college age kids right now who are. The oldest one is in graduate school. The next one is a junior who's interested in mathematics, graduate school. And the final one is the youngest is a high school student still looking at colleges. And high school, there's this incredible focus on getting into colleges. It's incredibly stressful. It's horrible. I just hate the process. Even my kids have been quite successful, but I still hate the process. And I particularly dislike the notion that colleges now do a holistic assessment of the student. So they both tell you it doesn't matter if you don't get in, but they say we look at all of you, and then we'll judge all of you. So those two things aren't really are somewhat in tension with each other. Right. And I think that's unfortunate. I think it's great. It's just psychologically important for people to be able to explore and find out what suits their interests and abilities. And I have a favorite example of this. This is getting somewhat dated because this is about 20 years ago when I first got here as an assistant professor. But I had an undergraduate who did some research with me. And he applied to graduate school, so he wound up coming to U of I as a physics graduate student. And this kid was great. He was, he had stellar undergraduate performance. He really got the physics, and he was really interesting to talk to, and he had a lot of things going on in his life. And during his senior year, he came to me and asked for advice on what courses to take. And he said, well, I could take this graduate course in physics, or there's a course in the English department in comic books. And I'm really interested in comic books. I said, look, this is the last chance in your life when you're going to have an opportunity to do this. You should definitely take the comic books course. And he did. And then he wound up coming to graduate school at U of I. And then after about a year, he decided he wasn't really that interested anymore in physics. And he left the field and he went to work at a company called G-Man Comics up in Chicago. And I have a paper with him, and his byline, his address is G-Man Comics, in Chicago. And he made a career out of that. So he now designs cards for games, and he's just been incredibly successful. So I think, it's not, I'm not trying to take credit for giving him that advice. I think he might have done the comic books course anyway. But I think it's an illustration of how taking a little bit of time to look at alternatives, look outside your narrow preconceived focus, can really offer benefits in the long run. Yeah. I'm sure he's much happier now than he would have been as a physicist. I had emails from him this year saying, "How you doing?" And, and I'm so happy for him. So I think that I think we're exposed to more and more as we go through life, and most of us don't have that bigger reach. When we're in high school, we don't know that broad a range of people. When we're in college, we're not exposed to all that many fields, although it is an opportunity to kind of reach out. Most people don't. And and so you always have to take time and learn about new things.
Like when you think about it, the solution seems simple. Like it shouldn't be this hard if you're a college student to just like explore and see what interests you. But today it feels like once you're in something, you're just supposed to just focus on it for the next 4 years. And that just feels like upsetting in many ways because
Well, it looks like you guys have found a way around it.
in some ways, yes, but still like
Yeah, I mean, we have some. I mean, even for like some classes, it just if you want to take the class, there are some people who just don't really like. You should take classes that are not supposed to for you to take, and they kick you out, and it just. I mean, it's surprising. I mean, I wouldn't expect that to happen, but I mean, if you try hard enough, you can definitely get around and just take those classes that give you different perspectives.
Yeah.
There's still a way. You have to go out a little more out of your way, but. Yeah, it is interesting, but I'm curious. What do you grew up doing when you were a kid? Like, what were you like as a kid? Like, what do you see?
I don't know if I'm qualified to answer that question, so I was a curious kid. I read a lot.
Like nonfiction, fiction.
Lots of different things. Lots of science fiction. Lots of nonfiction. So I was interested in history, which, I wound up taking a lifetime interest in. And I think what I read then as history is not what my wife would consider history now. But I was in middle school at the time of the bicentennial, the U.S. bicentennial, and that was a time when everybody was talking about American history, and so I read a lot about American history at that time. Again, I don't think I had a particularly broad background. I mean, I grew up in Massachusetts in a fairly affluent community, not a super affluent community. So there were certainly a spectrum of people that I was exposed to, and some of whom I'm meeting this weekend on Zoom for a reunion. But I did try and reach out and experience new things, to go to summer programs in other places, to meet new people. I think the internet would have been an amazing thing for me. It would have changed my life because I've been so curious. I would have gone down the rabbit hole in all kinds of directions at that time. Maybe it's a good thing I didn't have it, so I could focus. I think focus is a big problem for people these days. I mean, certainly for me personally, and I think for most students that I interact with, it's a problem to shut out information. Actually, there's so much that's available, so much attention-grabbing information available on my screen. So anyway, so I don't know what I was like to hang around as a kid, but I did well academically. And I have a brother who I was, always close to me in age, and we were always competing with each other, and that may have been an element of my development, which was important. And then I had a father who worked at Bell Labs, and he helped design the long-distance phone system. So there were devices that he built for the analog long-distance network that was in use at the time. And so he would, sit down at the dinner table after dinner, and he'd pull out a computer that he got at the office, or one of the first HP calculators. Okay, that was really cool. The first one wasn't programmable, the next one was programmable, and you can play Moonlander on it. So I learned how to program from that, and I learned that technology was really cool and interesting. So all those things might have set me off in a particular direction.
We actually talked to someone who worked at Bell Labs too, and he's a professor here. Is your brother doing physics in some way, or?
He's a heart surgeon, so he's the chief heart surgeon at Johns Hopkins.
Wow.
Yeah. but he does some engineering actually. So he also has had some startups that have designed and marketed surgical devices to help with some of the operations that he does. I also worked at Bell Labs. When I was in graduate school, I spent a couple summers at Bell Labs. And I worked in the radio physics group, which is the people who found the microwave background. It's the leftover echo of radio waves from the Big Bang. And that was amazing, because I would sit down and have lunch every day with a Nobel Prize winner, and there's like 5 of us around the table talking. It was super interesting. And that was great because I was in graduate school at Princeton, and people there were very focused on theoretical stuff. And then at Bell Labs, people were very focused on technology and how do things actually work? There's a very engineering perspective. So I showed up there, and they threw some stuff at me and said, this is going to be your terminal, and you have to change out some chips and upgrade it. And so I had to solder something on my first day there, and then I did a lot of sort of data analysis work on that terminal. And we'd sit around at lunch and talk about things like one of the guys I worked with had a Porsche, and how the door hinges in the Porsche were made. And he was interested in everything. So that was also really a broadening experience. Yeah.
The lunches at Bell Labs were very interesting. Are you aware of Richard Hammond?
You mean from the car guy? That this is.
No, but so Hamming, he.
Oh, Hamming. Oh, yeah, okay. I thought you said Richard Hammond.
No.
No. Do you know who that is?
No.
Oh, okay. Then I won't. He's on this British show of 3 obnoxious guys who travel around the world in cars, and they got kicked off the air for doing inappropriate things. Anyway, so Hamming, yes, Hamming codes, yeah.
Yeah. So he wrote this very interesting essay, You and Your Research. And one thing he would always say is that how interesting the lunches at Bell Labs were.
Mm-hmm.
And one interesting story he shares is that he would so he was a mathematician, but he would sit at the physics table, and he would talk with all these people that were super interesting, and then they all got Nobel Prizes, and they all left and whatever, and then he would go and sit at the chemistry table, and they would see that they didn't really make any progress. So he would ask a question, what are the important problems of today, and what problems are you working on right now?
Yeah.
And at one point, I think he got kicked out for asking that question. And then 8 months later, one of the guys came up to him, thank you for asking that question. At first, I didn't like it, but now I got promoted to X, Y, and Z.
Yeah.
So that culture of Bell Labs is just something that it's not really I don't really see it anywhere else today. But it was such an interesting culture, about what happened there. Very unique thing.
Yeah, there have been a lot of attempts to reproduce that, and I just think that it was a product of the time and the financial sort of structure of Bell Labs, which had a lot of resources because they had a monopoly in the phone system, and as part of the consent decree that allowed them to operate as a monopoly, they had to spend a certain amount of money on research, and then just some really visionary people running the place. They're just amazing. So radio astronomy, for example, started at Bell Labs.
Yeah,
there was someone named
accidentally.
Jansky. Yeah. And then another important radio advance was the microwave background research, where Penzias and Wilson used the antenna that had been used for a satellite experiment that Bell Labs did to measure the temperature of the microwave background. And a lot of things like that were very, very expensive by the standards of the day, but these guys were given the tools to play with, given the resources, and they were able to do something with it. And I think that nowadays, for better or for worse, there are a lot of places with the resources to pursue interesting ideas. And there's actually a lot more going on now in physics research and computer science research and all than there was then. It's just that we look back with the benefit of hindsight and know that all the foundational work was done there.
Where would you want to work at today if you were a college student and you were perhaps in physics or
in physics? You mean where would I want to go to graduate school, or where would I want to
work?
Where would I want to work?
Or just...
There's a ton of things going on in astrophysics. It's kind of a golden age of astrophysics. There's lots of new data coming in, lots of new parts of the universe that are accessible because of new technology that weren't before. Like James Webb. I was just about to say James Webb. So I, like many people, had my doubts about James Webb and whether it would actually work, especially given the Hubble fiasco. And so you know the story, right? That Hubble went up and it turned out it was out of focus because the mirror had been ground to the wrong shape.
Right.
And then someone had to go back and put in a pair of eyeglasses so it could see in focus. And so given that record, you might well have wondered whether James Webb was going to work, because it's a much more complicated instrument, especially with the primary mirror unfolding and then the heat shield unfolding, both astonishing things from a mechanical engineering perspective. So anyway, there's a lot going on in astrophysics, and there are lots of departments that are doing interesting things. I think what I know now, which I didn't fully appreciate when I was an undergraduate, is how important the sort of personal interactions are to your research success. So if you wind up in the wrong environment, it can definitely damage you and remove your interest in pursuing research. And if you end up in the right environment, it can lead you in completely new directions. And so that's an aspect of graduate school and research that's very hard to study. Not hard to anticipate, but it's really, really important in determining success. So I don't know, there's all kinds of opportunities, lots of it linked to information technology. So new data, new ways of processing data, big new machines, interesting new algorithms and machine learning, lots to do.
Let's say you had the option to work at either NASA or SpaceX.
NASA or SpaceX.
What would you choose?
I don't know. The key question is what you're going to be doing at each of those places.
Let's say you can do anything you want.
Anything I want.
You have the freedom to choose what you want to do.
Well, NASA has really interesting projects going on right now. So, from the standpoint of an astrophysicist, the person I am now, I think that I'd probably work for NASA.
What would you work on if you worked at NASA?
Yeah, let me give you a flip answer first, which is that NASA has the coolest job title in the world for a few people at NASA. And the job title is Planetary Protection Officer. And
okay, it's Space Force?
No, it's NASA. So that person is charged with preventing biological contamination from one planet to another. And I don't know how effective they are, but you cannot have a cooler job title than that.
Planetary Protection Officer.
Yeah, Planetary Protection Officer. So that would be my dream job title. But in terms of what I would actually want to work on day to day, there are people at Goddard Space Flight Center who do things which are very close to what I do now. So theoretical work that's relevant to planning NASA missions. And so I think that's super, super interesting. So that would be the easiest thing for me to go and do. In terms of uh, things are sort of outside my current bubble. I'm quite interested in planetary science, and I wouldn't mind getting involved in some, new mission to Mars, mission to Venus coming up in the late 2020, early 2030s. So I wouldn't mind, doing something there. I think being a professor at a university, though, is a pretty good gig because I can decide what I want to work on. And for the most part, I'm not super constrained by, obligations, or there's no boss who tells me what to work on. There's no one who can tell me what to work on. If I decide that something's not interesting anymore, I can go work on something completely different. And that's changed a little bit in the last 5 years because I've been working in a big collaboration called the Event Horizon Telescope Collaboration. And in a big collaboration, you have to be a team player. You have to work with other people, help other people out, spend a lot of time on things that you don't need to spend time on as an individual investigator. You have to sit in a lot of committee meetings. And I think that if you work in any big organization like NASA, if you're working on planetary exploration mission on Surveyor or something, then there's a lot of sort of working with other people in a very constrained way to advance the mission, to make sure everything works, to make sure what you're doing for the mission doesn't impact some other important aspect of the mission negatively. And that's a particular kind of work. Some people enjoy doing that. I'm sort of more of a scout. So we go out and scout the intellectual frontier and try and bring back something interesting as sort of an individual when we're a university professor. So there's some trade-off there in going to work in a big organization like NASA or SpaceX. If you go to SpaceX, you're working for Elon Musk.
You consider that a good thing or a bad thing?
I'm sure there are people who have great jobs who work for Elon Musk. I work for the governor of Illinois, actually. So, again, that's something that some people consider a good thing and some people consider a bad thing. I had friends who got their degree from the University of California, their PhD, and PhDs in California are signed by the governor. And at that time, the governor was Arnold Schwarzenegger. So they have their PhDs. So I think it depends on the answer to your question, whether it would be great to work for Elon Musk or not, probably depends on who's between you and Elon Musk. I think working directly for him would be extremely difficult. And I think most of us probably agree on that. I think working, in the organization several levels below him is probably just fine.
What do you think about, going to Mars and just, like building this new rockets, which is not really your focus, but in a way it is, because humans going to space and that, like, people being interested in space, without the rockets, probably like people would not be as interested in space. Without going to the moon, probably people would not have been as interested in space. So what do you think about going to Mars, going back to space, the reusable rockets, all that industry that's somewhat new, that kind of resurvive?
Yeah. It's remarkable. The price of a kilogram of stuff in low Earth orbit has gone down really dramatically. I think it's around like $1,500 or $1,800 a kilogram now. Yeah, so that's pretty interesting. And even from the perspective of someone like me who might be interested in science missions that are going to space, that means a whole new range of activities are now accessible in space. So that, I think that's good. I think it's good that there's competition, and it's not just SpaceX. There's Blue Origin. There's Virgin Galactic. There's I've forgotten what their name is, but they just had a launch off Wallops Island in Virginia. So another commercial launch company. There's a lot of opportunity there. I think some of this is driven indirectly by information technology, in the sense that it's easier to put together a really large, complex system like a rocket when you can model the whole thing on a computer ahead of time and anticipate a lot of the problems that would cause, when people were trying to launch Vanguard in the 50s, would cause those things to blow up on the launch pad. Anyway, it's all great. And I watched the Falcon Heavy launch a couple weeks ago, and it was just spectacular. They have these two boosters on the side, and then the core rocket, and the boosters go up and then they split off, and they're liquid fueled boosters. These aren't solid rocket boosters like the old shuttle. And then those things come down and they both land together, pop, pop, which is just, science fiction from my point of view.
Okay. That has become normalized today, which is like if you go back just maybe 5 or 10 years, you would think that's one of the biggest things you could possibly achieve.
Yeah.
And now it's just normal. SpaceX does it every time, and
yeah, multiple launches a week. I don't know.
Yeah, last year they had about 60, so one every week or so.
Yeah,
which is insane.
It is insane. Yeah,
and
so they're getting really good at it. I think. Yeah, that experience is invaluable.
I watched landing, just oh my goodness, this is insane how they just
they stick it,
figure it out, and just every time it's just boom, 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 boom.
Yep.
Nothing happens.
Yep. Yeah, so that was not the situation when I grew up, and the shuttle was launching. I remember shuttle going up for the first time. Really exciting. In fact, I was, I was 4 years old or 3 years old, the first moon landing, 4 years old. And I watched Walter Cronkite, who was the voice of reason on the network television in those days. I watched him on a black and white TV, and we saw the moon landing, and everybody was really excited about it. But that was, a big deal. There's a huge fraction of the economy got redirected into the Apollo program to make that happen. And then shuttle, which just never worked very well at all. And one of the most traumatic events from that period was the shuttle loss on launch. And I remember that very well because I was a junior in college at that time, and I walked into the dining hall. I had to check in with a lady behind the counter, Audrey, who was a very friendly, nice woman, and she mentioned to me that the shuttle had blown up, and I was just like, "You're kidding." So actually, I think that my experience leading up to when I was about your age was that NASA had a lot of failures, and it was discouraging for someone who watched Star Trek and read a lot of science fiction and so on. But now, SpaceX is great. Yeah, I think the price per kilogram coming down like it does will change things dramatically. There is there's some negatives to this. So one negative is that for optical astronomy, the low cost of launching things into space has become a problem, because there are a lot of shiny objects up there which go across the field of view when astronomers are taking observations. And almost every image that's taken has streaks across it from satellites passing through the field of view now. So it's a constant problem. And then the other problem is space debris, which you may know about. So So the amount of space debris is gradually increasing, and there's a spectrum of sizes of these things. Some of it's very small, but even a paint fleck moving at orbital speeds can gouge a window significantly in a spacecraft. And then if the volume of space debris rises enough, there's an instability that occurs where it's kind of a chain reaction. So let's say two satellites run into each other and produce debris. The debris then spreads out and runs into other satellites, which then also disintegrate and potentially, if there's enough of that, it could deny us access to low Earth orbit at some point. And this space debris problem really has to be managed in the future. And it doesn't help that there's also people trying to develop warfighting capabilities in space, and people testing anti-satellite weapons. So the Chinese did this a few years ago and produced a huge shower of debris in low Earth orbit.
Right.
Yeah.
How close do you think we are to traveling at light speed?
Traveling at light speed, a long way.
Like, let's say we want to go to Alpha Centauri. What would we need to have invented to make that possible?
Yeah, imagine it's possible. What components made it possible?
Yeah.
You have to guess, because obviously we don't know. So just I guess.
Yeah. So there's various ways in which it might become possible. So there's a group working now on interstellar exploration, and
what's their name?
I think it's called the Breakthrough Starshot. I'm sure I've got the designation wrong, but the notion is to put a very, very small spacecraft out and have it pass another star and broadcast images back of another planetary system. And I think one of the key notions there is that the spacecraft would be accelerated by a light sail.
Right.
And so you can use a laser that's sitting on the surface of the Earth, which is connected to some large power plant, like a nuclear power plant or something, and can broadcast lots of energy and momentum at the light sail. And so, some aspects of that are very interesting and seem reasonable, and some are going to require significant new innovations. So there's a lot of hazards out there. So interstellar space is permeated by debris, little flecks of soot. And if you run into that going at even 1/100th of the speed of light, then you have a problem on your hands. In terms of faster than light travel, sort of a la, Star Trek, warp factor 10.
Star Wars hyperdrive.
Or Star Wars hyperdrive. I just don't even know where one would start. There is a paper by a guy named Alcubierre, who's a relativist and who works in, I believe, Mexico City now. And he has this notion of a drive, but it requires the existence of matter, which sort of violates some of the really important properties that we think matter ought to have. And there's just no way of creating that kind of matter.
You said existence of matter or antimatter?
Well, so now I'm having to draw on this all from memory, but I think the idea is that you need matter with a negative density to make this happen. And that's just not really possible. So it violates lots of sort of long-held important principles in physics. So I don't know, but maybe someday, someone will figure out a way to create that and build one of Alcubierre's warp drives.
Because I'm sure people are thinking about this around the world. Like this is like, even though right now it seems like not feasible, but just the possibility of it existing and just trying to work it out, I think that's like, even reading it can be inspiring to many people, just like to get into the field or just
yeah,
as a thought experiment.
I get it. I love the science fiction movies. I love reading science fiction, but I also think that there are things that are possible, and there are things that people think are impossible that later become possible, and then there are things that are just impossible. And I think this may be in that category.
So one of the questions I've been thinking about is, where does gravity come from? And like, people have theorized the existence of the particle of gravity, or graviton.
Yeah.
But I'm curious to know what your view is on it.
Where does gravity come from? So, I could start that at various levels. I mean, we know that massive bodies produce gravitational fields, and
the bending of the space-time.
Yeah, but even Newton basically had it right. He got 99% on the gravity exam. I mean, his theory describes a lot of what happens in the universe. And then Einstein's theory produces some interesting and really important corrections. So corrections, for example, that are important for making the GPS work on your phone. So the relativistic corrections would, if they were not accounted for, would put GPS off by miles after a few days. So Einstein gave a description of gravity, which was famously geometrical, the curvature of space-time, as you said, giving rise to or describing the gravitational field. And then I think what you're alluding to is what happens when you think about both quantum mechanics and gravity. So you guys have probably had quantum mechanics, or at least been exposed to it at some level. And quantum mechanics provides a remarkably accurate description of much of the universe. And the one thing that it doesn't play well with is gravity, which is a very classical theory. And I think one of the central mysteries in physics right now is how you merge gravity and quantum mechanics.
Relativity and quantum mechanics.
General relativity, which is Einstein's relativistic description of gravity, and quantum mechanics. And we know that general relativity doesn't work everywhere, because if you solve for the structure of space around a black hole and then extrapolate inward through the horizon of the black hole to what's called the singularity at the center, there's a singularity in Einstein's, in the solution to Einstein's equation. And the singularity here manifests itself through tidal forces. So we're used to thinking of the tides, as providing a sort of gentle distortion of the ocean due to the pull of the moon. But when you have very dense matter, you can get much stronger tides, to the extent that you would experience tidal forces pulling you apart if you were close to the center of a black hole. And there's a great short story about this by Larry Niven, where someone flies by a neutron star and forgets about the tidal forces and gets killed by the tidal forces in their spacecraft. They fall from the middle of the spacecraft to one end to get squished. And that illustrates the kind of thing that can happen in extreme tidal fields. And as you get closer and closer to that central singularity, the tides go up and up. and they become formally infinite in the black hole solution to Einstein's equations. And we don't really think that can happen in nature. And at some point, quantum mechanics has to intervene and, somehow smooth out that singularity. So that whole question of the interaction of quantum mechanics and gravity and what it means for black holes has been an area of intense activity in theoretical physics for a long time now. It's not really what I work on. So what I think about is sort of black holes in an astrophysical context. So you put a black hole in the middle of the galaxy, and what does it look like? What happens? How does it interact with its environment? And most of the work that I do is purely classical in that sense. So we don't worry about quantum corrections to the gravitational field of the black hole because they're probably very, very small. Yeah.
If you had to explain what a black hole is to a kid, how would you explain it?
Yeah, so I do this, and I love talking to kids about this because they're not afraid to ask questions. They don't feel like there's anything that they should know, so they're just they're willing to go out on a limb and ask just the right questions. Yeah, so I would start by introducing the notion of an escape speed. So what goes up must come down. We all know this, but it's not quite right. If I throw something up at 100 miles an hour, which would be a pretty fast pitch, then it'll go up a ways and come back. But if I throw something up at like 25,000 miles an hour, then it'll be exit velocity, and it'll just go on, and 25, it might wind up orbiting in the around the Earth or in the solar system. So it would have escaped from Earth. And that speed, that escape speed is characteristic, as I'm sure you guys know this, but is characteristic of an object with a particular mass and radius. And so, people realized this at the time of, late 17th century, up about 1800, Laplace understood this. Other people understood this, so you could calculate this escape speed. And people realized that also that light only travels at a finite speed. People were able to figure that out by watching the moons of Jupiter, and they could see the clock formed by the moons of Jupiter ran at a slightly different rate when it was far away and when it was close. So you could use that to work out how fast light traveled. And so people knew speed of light was finite, and they knew about escape speed. And so that naturally leads to the question, is it possible to have something which has the right combination of mass and radius for the escape speed to exceed the speed of light? And then it would be a so-called dark star. And that's what a black hole is, basically. It's something that's where gravity is so strong that light can't escape. And then there are a lot of sort of corrections to that Einstein's theory provides. So Laplace didn't understand Einstein's theory. Laplace was long before, 115 years before Einstein. But Einstein's model produces basically the same result. You have something where the gravity is so intense that light can't escape. So that's how I'd explain it to a kid.
I think the kid would still be very confused.
Okay.
So, a couple of things. So, a dark star, which you say, it's basically escape velocity, like more than escape velocity, and like just trap pretty much. Like even though how fast you could be going really really fast.
Yeah.
You still get trapped no matter how fast you're going.
Yeah, that's right.
It would light, of course, which is the fastest thing that we know.
No, well, so this light having the things not being able to move faster than light is pretty foundational in physics.
Right, sure.
And it's electromagnetic waves happen to travel at that speed, but it's sort of built into the structure of space and time that you can't go faster than that. So, so
Light is
nothing.
the limit, right?
Light, nothing, no particles, nothing can escape.
Everything gets in there.
Yeah.
Why would that ever form? And then another question there is like, when was the first time we actually saw that? And the other question that is sort of related is, could we create such thing?
Could we create a black hole? Okay, so there are three questions there.
Yeah.
And the first is about black hole formation. And that this is an area of really active investigation in my field. So my colleagues and I spend a lot of time on this kind of thing. And there are multiple routes to making black holes, as was realized, 40 or 50 years ago. One of the most common routes is probably through the collapse of a very massive star. So stars, have finite lifetimes. They have nuclear fuel, they burn it, eventually they run out of fuel and they go dark. And for a star like the sun, that means a particular sequence of events at the end of its life, but basically the sun, very far in the future, will end up as what's called a white dwarf, which is just sort of an ember of it's ash left over from the nuclear burning. But stars that are more massive than the sun will go supernova at the end of their lives, so they'll blow up. And for some of those stars, for moderate mass ones, they blow up and they leave behind what's called a neutron star, which is like a giant atomic nucleus with very, very dense. But then if you start with an even more massive star, then probably at the end of their lives, those stars collapse and they make a black hole. And that's a very plausible route to forming a black hole, and one that actually may have been seen in the sense that if that were to happen, the star might just wink out and disappear. And people have seen stars wink out and disappear. It's not absolutely clear they were collapsing to a black hole, but that's a plausible explanation for what was seen. So that's one route to making a black hole. So another route is to just put a lot of stuff in one place. So much more mass than is in an individual star, and then it just can't support itself against gravity and it collapses. And then yet another route to making a black hole is to start with two black holes and merge them. And that's probably an important process in making really big black holes, so-called supermassive black holes, like the one in the center of our galaxy. So there's a lot of ideas about how you make black holes.
Artificial one?
That's the third question, so I'll get to that in a second. So then you also asked about when was the first time we saw one. And, it depends on how you define we saw one.
Yeah, so maybe not seeing, but become aware of such thing.
Yeah, so the first sort of foray into this was by Schwarzschild. So Schwarzschild was this polymath who invented all kinds of important ideas in optics and mechanics. And Einstein's paper came across his desk, and Einstein had written down these equations, which are famously difficult to solve. People only figured out how to solve them numerically in 2005. And he looked at this and he said, I think I could solve it. So he wrote a paper. He found a solution, which is the Schwarzschild black hole solution, and published it almost immediately as soon as Einstein's paper came out. And there's this humble brag in the article where he says, "Oh, it's always nice to avail oneself of exact solutions when they're available," and he found this exact solution. So there's the theory side very early on, and then people didn't really understand what black holes were or what context they might appear in astrophysics. And then in the 1960s, people found these quasars, or so-called active galactic nuclei, quasars. So very bright objects that were very far away. And it was quickly realized that one way of powering these things was through dropping matter into a black hole. So it turns out that if you want to just get radiant energy out, it's way better to drop mass into a black hole for a given amount of mass. You get the most radiant energy out by dropping it into a black hole, rather than, even if it's gasoline, you get much more energy out by dropping it into a black hole, much more energy out by dropping it in a black hole than fusing hydrogen into helium, which is what happens in the middle of a thermonuclear weapon. And so it provided an efficient way of taking matter and turning it into the radiant energy that was observed. So that was probably the crucial step, and that excited a lot of interest in black holes in the 60s and 70s.
And I think, if I remember correctly, I think there was an observation made where I think it might be a star or might be something that was just moving in a path it wasn't supposed to. And there was nothing there which explained why it was doing that. And I think that just led to people, I think they then back calculated how much mass
has to be there, yes.
Be there, and then
that's one way that people look for black holes, yeah. Yes. So so there are a lot of milestones along the way to finding black holes. So there's the quasar stuff in the 60s, and then the early 70s, there was X-ray astronomy. People saw unexpectedly bright X-ray sources. And turned out that those, like SIG X1 is one of the famous objects like this. It was stuff falling into a stellar mass black hole from a companion star. And then, various advances along the way, ultimately leading up to what I think is sort of the definitive proof, which is a picture of a black hole, which is what we did in Event Horizon Telescope collaboration. So that was the second question. And the third question was about making a black hole. And, when people were building the LHC, which is a big particle physics experiment in Switzerland, there was someone who wrote a paper that said, well, when you turn this thing on and you collide these particles, they're going to turn into a black hole. There's a chance that they're going to turn into a black hole. And so committees were formed and, people had to think about this carefully and write a reasoned response. And basically the simplest response is so simple that and so persuasive that you immediately know you have nothing to fear from an experiment like LHC, which is that LHC actually operates at pretty low energies compared to the energies that are available in a cosmic context from cosmic rays. So there are really energetic cosmic rays that hit the Earth all the time. And as far as we know, they don't form black holes. And so, this experiment is done by nature a lot, and we know they don't form black holes. So I think that's the context in which making black holes artificially has come up. And I don't know of any improvement in the black hole manufacturing technology since then. It's quite difficult to make a black hole because matter doesn't want to be compressed that much.
It would be funny if there was a Silicon Valley company that manufactured black holes.
I'm sure someone would try faking it until you make it on that one. You could probably raise venture capital. So.
I'm thinking of benefits of it, like what you can throw trash in black holes. I don't know.
Yeah. So there's this famous diagram in like the core general relativity textbook, which talks about getting energy out of a rotating black hole. sorry, we all know that when you spin something up, it has kinetic energy,
Right.
and you can store kinetic energy. You can store energy in a flywheel, for example. And a black hole is no different. You can spin it, and you can spin it up almost to the speed of light. And if something's moving at the speed of light, then it's the energy it contains is of order the mass times the square. This, it's mc squared. It's mass times the speed of light squared. And so you can store a lot of energy in a rotating black hole. And that is connected to what we think is going on in many quasars, which show jets of material coming out of them. And those jets are probably powered through a process that extracts energy from a rotating black hole. So nature finds a way to tap into that.
I think it's a conundrum because we think that nothing can travel fast, like at the speed of light. There are like very few things that actually do, and then we claim that black holes might rotate at the speed of light, or like
or close to. Actually, they probably don't. So it's not clear what you mean by the speed of a black hole because there's sort of nothing there.
right.
At some level, the angular momentum is in the space-time itself. But people are troubled by the idea of getting energy out of a black hole. And the way that works, the sleight of hand that we do is we don't actually, take anything out of the hole. What we do is dump something in with negative energy.
Right.
And then if you do that, by conservation of energy, what's left behind must have more energy, right? So you somehow made this into a negative energy object. So this thing has to have more energy. And then you can remove this thing to a large distance where you can use the energy. And you can do that with particles, which is something that was discovered by Roger Penrose in the 60s. Or you can do it with waves. Or you can do it with magnetic fields, which is the way that we think it's actually happening in quasars. We use waves.
How much is Stephen Hawking's work being applied or being used today in, let's say, your field?
Yeah, so in my field, it doesn't have a big impact. In sort of theoretical gravitational physics, it's absolutely foundational. So if you're just trying to construct models of black holes in nature, the processes that he described are not very important. So one of the things that he's best known for is Hawking evaporation. So the evaporation of Hawking radiation, evaporation of black holes. And the notion that arises from mixing quantum mechanics and gravity.
Right.
So you have a one-way membrane, which is the horizon of the black hole. And then a feature of quantum mechanics is that you can have pairs of particles appearing from the vacuum and then disappearing. It's expected to happen all the time. And most of the time they appear and then they disappear and no one is the wiser. But if they appear and disappear, if they appear and one of the pair of particles happens to fall into the black hole, then you're left with a real particle all of a sudden. And that's what produces Hawking radiation. Now, unfortunately, Hawking radiation produces radiation at very, very low frequency. So it produces radiation with a wavelength which is comparable to the size of the black hole. So black holes can be anywhere from 1.5 kilometers in size if they're the mass of the sun to much, much bigger than that. And so electromagnetic waves with a wavelength of 1.5 kilometers are really, really low frequency. And in fact, they're screened by nearby plasma. So those things, basically the stuff falling into the black hole will shut down this Hawking evaporation process. And it won't happen. And in addition, it's very, very slow for astrophysical black holes. So even if you set all those concerns aside about stuff falling into the black hole, just a black hole sitting in the middle of the cosmic microwave background radiation will gain mass much faster from that radiation, from those photons falling in, than it will lose from Hawking radiation.
Why is it called black hole? Like, where does the name come from?
Oh, there's a whole story there about who originated the name.
I think it was a
And
research paper that was published or something, right?
yeah, so there's a physicist named John Wheeler who worked at Princeton who really popularized the name. And it's not quite clear who suggested it to him. It might have been
Right.
someone at a seminar that he gave in New York. And it's a great piece of marketing. And black hole, it's actually quite an accurate description of the object. So great marketing. People used to call them frozen stars, which doesn't really capture the physics, and it doesn't really capture how they appear either. They're not just stars that are, fixed somehow. They're dynamical objects. They evolve, they gain mass, and things fall into them. And they don't. So the original notion in the frozen star interpretation was that stars collapse and then time slows as the collapse approaches the event horizon scale. So for an observer, if you watched a clock that was placed on the surface of the star, it would appear to tick slower and slower as you watched from large distance. If you were with the clock, unfortunately, the clock would just appear to tick at the same rate. Yeah. So there's nothing magical that happens. And so people interpreted that as the star becoming frozen. And that's, not the sort of modern way of thinking about it.
But you're right. A black hole has it makes you want to learn more and just
Yeah.
black hole, or like do you fall in there, or
Yeah.
like what happens?
Yeah.
Along with that, you kind of mentioned that time slow down. It slows down as you get there, almost to, or either slows down or stops at some point. So what does happen? And perhaps I should know this, but I don't know. What is time?
I think that's also something that is a topic of investigation. What is time? And what is the origin of the arrow of time is something that both philosophers and physicists think about. And I don't have any particular insights to offer you there. So that's really all I have to say about that. I mean, I don't have any deep insight into the nature of time.
If you were to want to figure it out, how would you approach it?
Well, I don't even know what question I would ask. The way I think about these things is very mathematical, because then I can ask precise questions and get precise answers. And one thing you learn in starting to study Einstein's theory of gravity and general relativity is that only certain kinds of questions are well posed. And so you learn to ask the right class of questions which have physical answers. And in many contexts, that means that mathematically you can model a measurement operation as something that produces what's called a scalar, which is invariant under coordinate transformations. And so that's my view of things. There's no that doesn't lend itself to some description of what time really is. I mean, I think for most of us, time is something that we perceive as, organisms, right? It's a gradual ticking away of our lives as we interact with each other. And I think that's probably the most profound and relevant description of time. So in physics, I guess one place where where you could ask a meaningful question about this is in the Big Bang. because that suggests that there's a
Origin of
origin.
time.
Yes. And what do you do with that?
What was there
What
before?
was there before? What was there before time? And it's not really clear how to answer that question, although there are some models of the universe which say that the universe expands and then it collapses and then it forms another Big Bang and then it expands
Singularity.
again. Yeah, exactly. And so those, it's interesting speculation.
Hard to find answers to.
Hard to find answers to. So the way physicists work at questions like this is to try and formulate an exact question and try and figure out what they can measure that would speak to that question. And formulating the question is a really important piece of it, and it's really difficult. I mean, it's just, I'm not being flip when I say, I don't know how to, I don't know how to turn that into something that a physicist can answer.
Yeah, in essence, it's not even about the problem itself, is that we just don't know what question to ask. And like you say, if you were to approach it in a more physics, mathematically way, what is a question that would give me a definite, quantifiable answer? And yeah, we don't know.
Yeah. So for example, in this bouncing universe theory, you might be able to calculate what the background of gravitational waves in the universe is. So maybe in the singularity, or near singularity, before the re-expansion of the universe, you excite lots of vibrations in the space-time, gravitational waves, and then those become part of the new universe, and they're there like the cosmic microwave background. And so you might try and estimate how big those gravitational waves are. And then you might try and understand what experiment you could use to measure the magnitude of that background of gravitational waves. And there are some limits on that background already from current gravitational wave measurement experiments. And then those probably give some, this isn't really an area that I work in, but those probably give some rather uninteresting limit on, the gravitational wave background. So anyway, I think a lot of what physicists do is try and take questions like that, which are interesting and appealing, and turn them into something that can be measured. And what we can measure is a really important part of doing physics, and that's sort of where the field, that's where the most important advances in the field occur. So, we can measure deviations in length between two arms of an interferometer extremely accurately now to sort of 1 part in 10 to the 23, thanks to advances in laser technology and all kinds of measurement technologies. And that's what led to the detection of gravitational waves in the first place a few years ago. So nowadays we can build sensors for telescopes that are much more sensitive than anything that was used in the 50s or 60s. So it was in the 70s that people started using CCDs for astronomical purposes. And that just completely changed the field, because astronomy went from being this qualitative subject where you looked at a photographic plate and tried to figure out what was going on, and you could actually measure numbers. And I think there aren't that many people around left who remember that transition where astronomy went from being a qualitative field to a quantitative field. But now it is. Now we think a lot about sensitivity of our instruments and what new things can be measured.
what advice would you have for a student like us who's motivated and curious to learn more about the universe, this place we live in, and just pushing the frontiers of our knowledge?
Yeah, so I think there's a lot of sources that you can turn to read about what's going on at the frontiers of physics. I especially like Quanta Magazine, which is this thing that comes out of the Simons Foundation, and they have just outstanding and very high level pieces. So I think they're better than Scientific American.
I follow
think
their
they're.
YouTube.
Do you?
YouTube
Okay,
is
yeah.
very, very, very well made. Like
Yeah.
they're like their videos are like they explain the concepts like extremely well. The graphics,
Yes.
the animation, and everything.
Yes.
Like, very well made.
Yeah. So I would say Quanta is a good place to turn to. And then, scientists love to talk about their work. So nowadays, it's probably not a problem of finding, well, it's a problem of locating information that's at the appropriate level. But there's a ton of it out there on YouTube alone, where people talk about, here's what we know and here's what we don't know. It's actually getting people to talk about what they don't know that's the really difficult thing, because no one likes to do that.
Exactly.
I think, I think there are books that are interesting. So a lot of popular astronomy stuff is a little too GWOW for my taste. I mean, I think, it's good for some people, but if you're trying to, get a hold of what is it that we know, what are the facts, what is it we're trying to learn, what might we discover soon, then, there's a pretty limited subset of people who are explaining things at that level. I think Neil deGrasse Tyson is absolutely fantastic. He's usually right on with his descriptions of what's going on in astronomy. And Phil Plait is another person who's really good in talking about astronomy. Katie Mack is fantastic. I don't know if you've read her.
I've heard of
her. Yeah, so I've just been reading her book, and I think it's great. And then I used to assign in my introductory astronomy course, the higher level introductory astronomy course, a book which is called Coming of Age in the Milky Way, which is kind of a story of modern astronomy. And I think that also, is super useful in kind of setting the stage. And the beginning of that book is just absolutely wonderful. It talked about the ancients, climbing mountains because they thought they would be closer to the stars overhead. And they are, but only by a very, very, very little bit, as we now understand. But you get a sense there, not only, for a little bit of what life was like, but also about the sort of oceans of things that people didn't understand that you understand now just by virtue of growing up in a time when we're absolutely saturated with information. Like you probably have, maybe you know exactly what the distance to the nearest star is, but you probably have some notion that, it's bigger than the solar system, that the stars are incredibly far away, that we know that the Earth orbits the sun. We know that the sun orbits the center of the Milky Way. We know that the Milky Way is just one of tens of billions of galaxies in the universe. We know that lots of the stars in our galaxy have planets around them. A very large fraction of the stars have planets around them. And all that, is the product of modern astronomy. It's given us something about knowledge about our place in the universe that didn't exist, certainly in my parents' generation. And it's just, that progress, that sort of opening of the window onto the universe is really wonderful. It's wonderful to be a part of astronomy these days, and to see it happening even as we speak.
I remember that, I think in the 60s or so, the theory about dinosaurs and how they died with the asteroid
Impact, yeah.
Right, it was new because like before people just thought they just died or something weird happened, but so that theory itself, like every kid, if you ask like dinosaurs, like they know it was an asteroid.
Yeah.
So that in itself is surprising. Like when I learned this, like wow, I would have never expected that to be something else other than the asteroid. Like we may not understand how an asteroid is or anything, but
Well, we actually know a lot about asteroids now because there have been sample return missions. The return isn't here yet, but yeah. So I mean, I understand what you're saying, but that's another area where we know an incredible amount now that we didn't know 10 or 20 years ago. And the extinction of the dinosaurs is interesting because it also gives you some perspective on how the Earth changes over time. We think one of those sort of civilization-destroying impacts occurs pretty often, like once every 60 million years or so, and it's just sort of random. It's like the luck of the draw. It's actually, one of the things that's motivating a lot of the big new astronomy surveys that are coming online now. So these big optical surveys where you take a telescope and you scan across the sky and you visit the same place on the sky repeatedly every few nights. One of the things that's motivating that is planetary protection. So not the kind of biological planetary protection that we were talking about earlier, but finding asteroids that might collide with the Earth.
I think last year they did some sort of experiment where they successfully deflated, I think is the right word, or they moved the asteroid away or something.
Yeah, so a lot of
there you go.
Yeah, so it was asteroid deflection. So instead of Bruce Willis, do you guys know the movie where Bruce Willis goes up and drills and tries to deflect an asteroid that's coming toward Earth?
I'm not.
Okay, classic. I've forgotten the name, but anyway, instead of sending Bruce Willis up to deflect the asteroid, you send up a spacecraft, and the spacecraft, collides, rams into the asteroid. And in this case, the asteroid was in a binary system. So in the collision, you could push on the asteroid and alter the orbit of the binary, which is something that's more measurable than just changing the orbit of a single asteroid. Yeah, so you should get the sense that life on Earth is a little bit fragile, and that the bad things happen over a long time scale. So, there's volcanoes, which are actually pretty frequent. There's enormous earthquakes. There's a course here called Astronomical Disasters, right, that looks at some of these things. So asteroid strikes, evolution in the very, very long term. The evolution of the sun is going to cook us. But that's far, far in the future, billions of years in the future.
What do you feel when you not took but capture the picture of the black hole? Like what did it make you think about like the universe and your place in it? Like, what do you feel?
So so that was a process that extended over many years. So I have many thoughts about this, but this is something that I had been working on from a theoretical perspective for many years, since like the mid 2000s. And what was amazing was that it looked just about the way we expected it to. Total surprise. And so there's a certain sense of wonder from that. So I wasn't involved in the team that produced the actual image that we see, that's been broadcast and seen by billions of people worldwide. but I was there at a conference of the people who were working on this when after the data had come in and people were beginning to look at the data. And we don't measure an image with the Event Horizon Telescope. We don't take a picture with a camera. We measure aspect of the image on the sky, which is called the Fourier transform.
Right.
So you can imagine taking this image on the sky and rewriting it as a sum of different waves, and we measure the amplitude of individual waves with telescopes, pairs of telescopes on the Earth. And so the raw data was just this, it's called a Fourier transform. So it doesn't look like an image at all. And what we saw was something that looked like absolute value of a Bessel function. And I remember standing there at the after talk cocktail party, and one of the Chef Dolman, who was the founding director of our collaboration, brought in his laptop, and we started talking about this, and he showed me this thing, and it went like this. And I was like, crap, it's huge. I can't believe it. And it was especially surprising because the first black hole that was imaged was in the galaxy M87. And in that case, we didn't actually know what the mass of the black hole was in advance, and therefore the size of the black hole, which is proportional to the mass. And the uncertainty was a factor of 2. So there were 2 estimates, a low and a high estimate. And if there was a high estimate was right, we'd be able to see the black hole. And if the low estimate was right, we wouldn't see it. And as soon as you saw this thing, I knew that it was huge, that it was the high mass estimate that was right. And so that was the aha moment for me. But I think one thing that Shep Dolman really understood very well, and that I understood not well at all, was the public impact of that image. You know, I've been working on this for a long time, and no one's really going to be interested in this. And it turned out to attract a lot of attention indeed. And I knew it was going to be a big thing after the image came out. And I went to pick up my daughter at swim team practice, and one of her teammates asked me about this. And I, well, you know, if it's getting around at this level, then it's really in everybody's head now. So I think that was another surprising aspect of it for me, was just how interested people were in this picture.
When are we getting the next one?
There's going to be, there are lots of them already in the can. So there's been data taken, the original images were based on data taken in the year 2017. And then there was also data taken in 2018. And then we have 2 additional years in the can, the most recent from 2022. So there's a certain time of year where the sources are visible in the night sky. And that's in the late spring.
You just focus. Oh.
Yeah. Oh, and I was just going to say that, you know, because of the way these measurements are made, you look at correlated signals between pairs of telescopes, and that gives you information about what's in the image, and we reconstruct the image from that. And so if you have, you know, 3 telescopes, then you have 3 pairs of telescopes. If you have 4 telescopes, then you have 1, 2, 3, 4, 5, 6, okay, and so on. And the, you know, asymptotically, the number of pairs scales as the number of telescopes squared. So adding new telescopes gives you a lot more information. And the 2022 campaign, we had a lot more telescopes. And so we expect that there's going to be a lot more information in those images. And you asked about images, But I think the really exciting thing is going to be movies. So this is coming. So the collaboration is building up the capability to go back and look at, say, M87 once a week for a few months. And then we'll be able to string those images together into a really nice little movie of the black hole. And that'll tell us tons of stuff about how material is moving around the black hole. And that will be almost as impactful as the original announcement. Yeah.
Do you focus on one black hole at a time, or are the telescopes like watching multiple sources while recording the data?
So while you're recording the data, you're pointed at one object for a certain amount of time. And then there's some interleaving with other sources, which are calibrators. So the sources of known brightness and very, very slowly. You go back to the source, then back to the calibrator.
One black hole, all the telescopes just like focus on one black hole.
Yeah.
Or like 1 year, or how long you're taking the data.
Right. So the campaign lasts around a week.
Okay.
And in each night, you might visit 3 sources or 4 sources. And then on the next night, go back to some of the same sources and some different sources and so on. And, we have, I think it's 4 nights of data on M87 from 2017.
Oh, so that was just, that image was based just on 4 nights.
Yeah. And most of it was based on a single night. So if we revisit, we're going to understand a lot more about the source. We'll have a lot more information.
So all the other time went into just processing all that information, analyzing, putting it together internally.
Yeah. So there are a lot of reasons. Yes. And there are a lot of reasons for that. This is kind of a novel kind of observation. We had to invent new algorithms for making the images. We had to understand those algorithms better than anyone had understood them before, I think. And we had to invent new methods for analyzing the data. And we were conscious that this was, if not a publicly significant event, at least in my case, certainly a scientifically important event. And so we had to, we wanted to make sure everything was correct. Yeah. So movies is the big thing that's coming next. I think that's a few years away, but it will come.
Yeah, I do wonder how anything, what that would tell you about, like, for instance, like you study like hot plasma and everything else, and like how.
Yeah. So what do we learn about from all this stuff? So there are a whole bunch of science objectives in this business. One hope is that we can measure how rapidly the black hole is spinning. And there have been a number of techniques proposed for this. And some of them are accessible with a movie. And others require more resolution. So there's this fact about the resolution of a telescope, which is that it's diffraction limited. And that means that the angular resolution in units of radians is equal to the wavelength of the light you're observing at divided by the diameter of the aperture. Okay, and this is true for Event Horizon Telescope as well, except the diameter of our aperture is the diameter of the Earth, because we have telescopes on opposite sides of the Earth. So there are 2 ways to get higher resolution. We can either reduce the wavelength, or we can increase the size of the aperture. And the only way to increase the size of the aperture is to go to space. So there's a number of proposals that are being discussed now for sending a satellite out that would have some kind of capability for observing and recording signals at the wavelengths that we use, which are 1.3 millimeters. So this is very, very high frequency radiation. So your microwave, as you know, is like 5 gigahertz, right? And then this is 230 gigahertz, so very high frequency. So so that may happen, but if that happens, it'll be in the 2030s. And
Wow.
it's a long
Not too
time.
long ago, 8 years. I mean, no, 7 years.
Yeah, I guess it's getting closer all the time, but eventually somewhere out there, I'm going to retire, and I'll watch from the sidelines after that. So that's one way of getting higher resolution data. Another way is to go to higher frequency or shorter wavelength, and that's hard because the Earth's atmosphere tends to get more and more opaque due to water vapor in the atmosphere. Right. As you go below that 1.3 millimeters in wavelength or above the 230 gigahertz that we observe at. And so you need a very good site, so high, dry site. And you need to be lucky with atmospheric windows. So you need to observe in a region of the spectrum where the Earth's atmosphere is relatively transparent. So that's under discussion now, and one of the next phases for EHT will be adding in the ability to observe at 345 gigahertz as opposed to 230. So that'll give us a little extra factor in resolution.
Why haven't we put a telescope on the moon or something?
That's what I was thinking.
Oh, okay.
We had logistical purposes, right? Like if someone had to like repair it.
Have you seen a proposal or anything like that?
Yeah, so people have been talking about this for some time. So let's see. So the disadvantage to putting something on the moon is gravity. Okay, so one of the things you fight in an observatory on the surface of the Earth is gravity. So you have some structure which has to be maintained at a particular shape, you know, the antenna basically, to within a fraction of a wavelength of the light that you're observing at. Okay, so you've got this thing, you've got it in the right shape, and now you tilt it. And you know, these big steel structures or carbon fiber structures are floppy, and so they come out of shape, and you have to design your telescopes very carefully to put them back into shape after you tilt them. And that's a huge problem on the surface of the Earth. And you would basically be reproducing that on the surface of the moon. And so the question is, why would you go and put your telescope on the moon when you could just float it out in space?
Right.
And then you don't have this problem. Yeah, there are other problems, but you don't have that problem. There's an advantage to going to the backside of the moon, which is that you're shielded from radio waves from the Earth.
Right.
So at certain wavelengths, it's, you know, the Earth is really noisy. And it's a problem for astronomical observations. So to give you an example of this, we were talking earlier about Bell Labs and that antenna that Penzias and Wilson used to measure the CMB. When I worked there, we used that antenna to make measurements of hydrogen in the sky. So 21 centimeter radiation is given off by hydrogen. And those measurements were partly corrupted. And they were corrupted because there was a spare radar that would be turned on at Newark Airport that operated at about that frequency. And when that thing turned on, you know, it would just blow this sensitive instrument away. You'd see this huge spike in the data. And so in the intervening years, the radio environment has not become quieter. And so that's one reason you might go to the moon. I think one sort of larger question about human activity in space and elsewhere in the solar system is how you protect the people who go out there to tend to these instruments from things like cosmic rays. So, you know, if there's a solar flare, it sends out high energy radiation, so fast protons, for example, that can penetrate and cause radiation sickness in astronauts. And to really shield against that, you basically need a shield of material which has the same material column is our atmosphere. Okay, so above each square centimeter of the Earth's atmosphere, there's about a kilogram of material. And that 1,000 grams per centimeter squared shields us from cosmic radiation. So that's really roughly what you need to shield astronauts. And so if you went to the moon, then you'd have this big rock underneath you, and you could burrow in the rock and hang out there safely, without being exposed to cosmic rays. If you're just in orbit around the moon, then you might run into trouble if there's a really big solar flare.
You said that the Earth was noisy. Why haven't we affected the sensors of other beings in the universe?
Yeah. Well, we probably have lit up, to the extent that there are any detectors out there, we would be extremely visible. And Carl Sagan wrote about this. The first really powerful radio signal to go out from Earth was the Nazi television broadcast of the Olympics.
Really?
So that's our ambassador to the outer space. And then another signal that's very, very visible are radars in Russia and the US that are pointing over the poles, which are supposed to provide early warning of incoming missiles. And so those things point up at the sky, and then the Earth turns, so they sweep out this cone on the sky that's exposed to these radars. So those two things are our ambassadors to the rest of the universe, leading the pack. I think that if there's a civilization out there at a technologically appropriate level, they would be able to see us.
So why was the TV broadcast so strong? And
yeah, I don't remember the details, but I know that out of all the broadcasts up to that point, that was one of the most luminous. Yeah.
Do you think there's people out there, or now, if I were to ask you that question 5 years ago, oh yeah, that's a dumb question.
No, I don't think so. Actually, I've never thought that.
With the UFO reports and everything, all that has been.
Yeah, I think that is crazy. Actually, there's a lot of interest among this now, among serious people. But I think that the UFO stuff, I'm sorry, I didn't let you ask your question, but I feel like that stuff is just insane. It's really hard to travel between the stars, no matter how anyone figures out how to do it. It's going to be difficult and expensive to do. This is difficult and expensive for you to buy a ticket to cross the ocean now. And I think that there are so many other possible explanations for what's seen. The number of encounters that aircraft have with other aircraft and odd phenomena are extremely large. There's a large number of pilot hours that are recorded, and so a few incidents are completely expected. Something odd happened in any, if you have millions of pilot hours, it would be extremely surprising if there weren't a few minutes in that millions of pilot hours that were really weird. And then in terms of whether there are civilizations out there or not, I think that's extremely plausible. We know now that lots of stars have planets around them. So probably at minimum tens of billions of planets in our galaxy, maybe 10 times that. and then tens of billions of galaxies in the universe. So if you multiply those two things together, you get a very large number. Like, it's almost as big as Avogadro's number of planets. So it would seem surprising if we were the only place where life had arisen and where some kind of, intelligent life that was capable of interpreting its environment arose.
And when you say the UFOs thing, it's crazy, and you think there's a different explanation for that. Why do you say that, and why do you think that people are so confusing? What exactly made the serious people actually think about it, and not as before, we just dismissed it?
Yeah, well, so my arguments are mostly kind of statistical, that there's a lot of encounters. Each year there are 7 or 8 billion people on the planet, and there are 8,000 hours in the year, and people have a wide variety of experiences in those 8,000 or more than 8,000 hours, more like 10,000 hours in a year, and people have a wide variety of experiences in that time. And some of those experiences are just strange and hard to explain, right? So again, I think that if you have a system which efficiently sorts those weird experiences into a single file, you're going to get a collection of really weird stuff. And that's my statistical argument. And I also think that people just want to believe, right? So people are very motivated to believe that we're not alone. So anyway, I'm predicting that there's a review committee looking at this stuff right now. It's being led by David Spergel, who's an astrophysicist. And I'm predicting they're not going to find anything new. And there's also the notion that, well, it's not in the publicly available data, it's all hidden by the military. I mean, come on, nothing gets hidden for long. Everything comes out. There really aren't many secrets that are kept by a large group of people. And a lot of people would know about this.
Especially now.
Yeah.
If it's probably out, it's probably out, but because we have so much information, it's just hard to filter through which one is actually the actual answer.
Yeah.
I believe there was someone who said, like the way to keep a secret is not to keep it a secret, but to actually just let it out and just give a lot of noise.
Hidden in plain sight.
Right.
Yeah.
It's like, oh, that was the thing? I thought that was obvious.
Well, there's also Ben Franklin's, which is 3 may keep a secret if 2 of them are dead. So, yeah. So, a lot of stuff comes out it's kind of surprising that it comes out. A lot of information about technical capabilities and so on. It's just really hard to hide. Yeah.
What is the thing? Yeah, like you said that people just believe things to believe them. A different way to ask it is that everyone worships something. Like everyone believes that thing. Like, what is that thing for you?
Yeah. So I don't think people believe it just to believe it. I think people have deep-seated needs that are, formed in their makeup from some combination of biology and experience and so on. And so that's, that some of those deep-seated needs, I think, drive people to believe. Another way of putting this is something that you hear religious people say, which is, there's a God-shaped hole in the human heart. And, as a human being emotionally, I understand what they're saying, but as a scientist, there's nothing to measure. There's, no test I can do to assess whether there's any action of, beings, supernatural beings in the physical world. So there's no evidence of that yet. Yeah.
Do you believe in anything, or used to believe in anything, or what's your stance on that question?
Yeah, so I grew up in a moderately religious household, and my family were Protestants who belonged to a particular sect of Protestantism called the Congregationalists, or UCC. And basically they're the descendants of the Puritans from New England. They're not like the Puritans anymore, though. So they're a very progressive church. Yeah. I don't know. I think there's evidence that religiosity is declining sharply in this country now, and I don't know if that's true around the world actually, but certainly in the United States, religiosity is declining sharply. So the number of people who go to church, number of people who will, attest on polls to believing certain things, and I don't know why that is. I think maybe it's because people don't live with death all the time in the same way that they used to. And maybe it's because we have more understanding of things in the physical world that used to inspire religious feeling in people. Maybe it's because people are busy watching Netflix. I don't know. I mean, people spend more time on Netflix now than they used to spend in church. So that's not just a offhand comment. It's Netflix is soaking up a lot of neural hours.
The point which you said about people, like the change in mortality rate, I think that's a very interesting point. I don't really associated the decline in religiosity with the mortality rate, because I can see how if like people around you are like dying at a very early age, it can make you want to believe in a higher power and find more meaning in life. Like it's like I've been reading this book which basically explained. So the book is not about that, but there was a part of the book which said why watches existed. Like, why did we invent watch? And it was basically during the Black Death that people started like finding more importance in life and just realizing how fragile life is and how important their time is. And after that, people started valuing their own time more, and they like made a device which would help them basically keep track of it.
Mm-hmm.
So that's how like the modern watch or the hourglass was made.
Mm-hmm.
It was like really interesting thought that
it was
like
coupled to people's experience of death. It may also have been coupled to in Europe. Europe was overpopulated probably before, and then things were better after the Black Death in the sense that people had more resources to live their lives. So it may have also sprung out of the resources that people had after that. I'm not a historian. I'm just speculating crazily. And as far as religious feeling goes, I mean, I'm here because I'm a professor and because I work on astrophysics. And I have special expertise on that, but I have no special expertise in psychology or history or religion. And so, I'm not sure I have anything that's especially useful to say about that. And I also think, there's this temptation for people who are experts in one area to like go out and talk about things that they don't really know much about because all of a sudden they have a platform. It's like celebrities. If someone can sing really well, all of a sudden people are interested in what their religious beliefs are or, what their dating habits are. And it just seems to me that, that's kind of an abuse of your sort of professional role to do that. So anyway, that's my take on the religious question. I don't really have any special expertise.
I agree with you, but I think there's also some value of, sure, you may not know as much as the quote unquote expert, but there's sometimes that no matter who you are, where you come from or whatever, or your level of expertise, that you can bring some sort of insight that the person who's the expert who read all the
Sure.
texts, but also
Sure. I mean, if your point is we shouldn't trust experts too much, Juan David, then I agree with that.
But beyond that, it was just people talking to people, and at the end, it just the conversation.
I guess I've seen instances of people sort of pontificating about things they didn't know much about, and that bothers me. And even in a narrow field that I work in, which covers the entire universe, there are people who are experts in black holes or stars or planets or a particular kind of planet, and their expertise. It's a common mental fallacy, right? To believe that if you're an expert in one thing, then all of a sudden you can jump out and make pronouncements on other things. And I just think, we have to follow through scientific method. We have to, be careful about what we think is true. We have to test it. We shouldn't throw aside our main tool in understanding the universe just for the sake of pontificating about something.
And to end our show here, we have a section called underrated or overrated, where we basically...
I don't think I got to the end of any show on your YouTube channel, so I didn't know about this. Okay.
Where we basically give you a prompt and you just say whether you think it's underrated or overrated. So the first one, the interstellar black hole, like the movie Interstellar, and how the black hole was portrayed in the movie. Do you think, if you have seen that movie? Yes. So that representation and just how it was presented, even though it was sci-fi and like there were some fantastical objects associated with it, but
I thought it was really exciting. I think it's rated about right.
Okay.
Is that an answer that's available to me, or? I organized a conference on accretion, and we actually had one of the guys who worked on the black hole visualizations for that come in and talk to us at the conference. And there were some really rigorous calculations that went into that visualization. On the other hand, here's the thing that bothers me. So you look at those pictures and you see something that looks kind of like Saturn's rings moving around the black hole. So it goes up and over the back and then around. And it's about equally bright on both sides. And so here's the thing. And that is not really the case. And in fact, it should be brighter on the side that's approaching you. So there's an effect called Doppler beaming, which makes things brighter when they're approaching you at the speed of light and dimmer when they're receding from you at close to the speed of light. And that should make one side much, much brighter than the other. And that was apparently what they were originally going to do in this calculation. And then Christopher Nolan said, that's going to be confusing for the audience. Take that out. And so there are some things in there that are, flawed from a purely scientific perspective, probably not from an entertainment perspective. I mean, he's the expert on what people are going to be confused by. And then there's like a library in the black hole and stuff. So I don't know.
Yeah. But like
crazy.
just that representation was just like, I don't think anyone has ever tried to represent it from that sort of scientific perspective. Like,
yeah, as accurately as that. Yeah, I thought it was fantastic. So I grew up with Disney's The Black Hole. I don't know if you know about this movie. I bet you can find it.
Right.
And at the time, the graphics were amazing. But nowadays, we look at it and we think this is absolutely awful, kitschy stuff. That actually made a little bit of effort to represent the black hole correctly. But if you put a scene from that movie next to a scene from Interstellar, it's just, what an advance. I mean, it just looks great. Interstellar looks great. Yeah.
fantastic movie.
Yeah.
I wonder how many kids will turn out to take, your future, you're the astrophysicist, Dr. Gammie job in the future because of that movie.
Yeah, I think there's a lot of that like Star Trek, Star Wars, movies like Interstellar get to people at a crucial time in their lives and spark some interest that people follow. Yeah, I think it's really important. Okay.
The next one.
You're next. Okay.
Yeah. So in one of your talks, you basically opened the talk in a very interesting way. So you said, here's what an AI would have come up with, and here's what I came up with the black hole picture. So generative AI, overrated or underrated?
Yeah, I think it's underrated. Yeah. So not today, but we're in the exponential growth phase for machine learning, and I think it's going to change a lot of things in our lives. It's hard to know exactly which things right now. I think that it's evident from Tesla that interactions with the physical world are really difficult and unpredictable. So Tesla's self-driving mode seems to be a harder problem than was anticipated, even with the resources that Tesla has put into it and all the hours of data that they've got, millions and millions of hours of data. But there are certain things like text processing. If you look at ChatGPT is a really good writer. If you ask it to write a 2-paragraph essay about something, it'll produce something which is just, better than most undergraduates can produce. And so there are a lot of jobs that basically consist of producing text like that. And, being a lawyer is one of them. So I think that, maybe there are other aspects of the law which lawyers will spend more time on than writing things up like that in the future. But I think there's going to be huge shifts in fields which just, read something, write something out. A lot of administrative work is like that. So I saw someone ask ChatGPT about future directions for a university, and it wrote this document which sounded exactly like the strategic planning documents that we see coming out of senior administration here. And it hit the 5 important points. And it was better actually than some of the strategic planning documents I've seen. So I think it'll have a profound effect just in the next few years. My student, so the thing that you referred to earlier about the opening of that talk, was a former student of mine produced that art. So it asked the AI to produce a black hole in the style of Starry Night, or I think there were two in that talk. So there was one at the end and one at the beginning, and one of them was a black hole in the style of Starry Night, and it produced a really beautiful image. And so that is something that I use in my talks because it's beautiful.
Yeah.
But I don't know. What do you guys think? Is
I mean,
are
so
mechanical engineers going to be replaced by?
there are two perspectives
Yes.
to see this. So there's one perspective where probably the one I hold, which is, this AI things will get you ready to make a decision. So like that would be like storing information, reading the textbook, doing the research. Like you could ask, okay, maybe not a good example. Like, hey, I'm interviewing Charles Gammie. Like, what question should I ask him?
Yeah.
And yeah, I could go read all the research papers and do everything else, but still I would not have that context that the AI would give me to ask the right question, which is what we're talking about. Like the problem with science and everything we do in life is not necessarily about doing the work. It's about asking the right questions, and I think AI will give us that enough context to ask really good questions that we wouldn't have the opportunity to do that. And then there's the other perspective of people who think that, like people still need to write essays for gen ed classes, and oh my god, if they don't write essays, they're not going to learn. It's like saying that kids before cars, they had strong legs, therefore we should now with cars they're going to have weak legs, therefore we should ban cars because they're going to have weak legs, when in reality having strong legs or weak legs doesn't matter because we live in a different world. So that's
well, it was a similar debate that occurred when calculators became available in the 1970s to school kids. And are we going to allow people to use calculators on exams? I mean, come on, they're not going to know how to add and subtract. And I imagine that something like that will occur now. But I think that writing is a little bit different because writing is sort of the most fundamental expression of thought that we have. And maybe some aspects of this can be replaced by video creation tools or something like that. But once you start turning over certain tasks to some automated process or to some other human being, you become unable to do those things. And I think it is true that people are much worse at doing calculations in their head now. Like I do this all the time in lecture. I talk through calculations, and if I do like 15 plus 32 on the board, then people have a hard time following that, right?
Really?
Yeah, I think so. Yeah. And maybe your education was different, but I think that there's people on average, not every individual, but the center of the distribution has shifted in your generation, people who are less capable of doing numerical calculations by hand because of calculators.
Right.
And you also know, if you've been in any organization, let's suppose you have 5 people who are doing something, I don't know, like your show here, and one of you is really good with some particular responsibility, like doing the editing for every show. I don't know who does that. And then you do all the editing, and let's say, I don't know how this works, and then you will find after a little while that you can't, you've forgotten how to do the editing. There have been a couple of software updates. The buttons are in different places. You don't know how to do it anymore. And so I worry that we're going to turn over some of that fundamental activity or thinking to these large language models.
That's what I'm also worried about. Like, I feel like, yes, these tools are like very powerful and can be used to create like really great things, but I'm afraid that it also might make us thinkers, because we have the answers at our fingertips. Like, it's so easy to just like ask and get the answer instead of like
Yeah.
us trying to even like try to think through it. Maybe then use the tool as a resource to maybe help us get through that answer rather than just giving us the answer straight up.
Yeah, so I think Google is another interesting, it's exactly the same kind of thing. The other thing about Chat GPT and similar tools is that you can ask it questions about things that you happen to know about, and it will speak with great confidence in perfectly written sentences and deliver utter crap. And it's impossible to distinguish. So Chat GPT, if you were to score each assertion in a paragraph, I don't know, sort of 1 in 10 or 1 in 5 of those assertions are just wrong. And so we need to have the capability of distinguishing which ones are wrong. So one possibility is that in the future, interacting with these things will be a big part of what people do. So that'll be their job. But AIs have to be trained, right? And I mean, they're not as complicated as people yet, but people have to be trained too, right? And to do that, we've constructed this whole industry of universities and so on. I don't know, we're going to have AI universities where AIs go to get trained. Are we going to have AI psychiatrists? Because some of them are going to head off in funny directions when they become complicated enough. I don't know. But underrated. Underrated. So.
Last one. The Einstein-Rosen bridge, also known as the wormholes.
Oh.
Underrated or overrated?
It is what it is. And if people, so I guess I would ask you what your rating is. If people believe that it's a way to get from one part of the universe to another, then I would say overrated. As a scientific concept and something that's interesting to study,
Right.
I would say it is what it is. It's interesting. In the popular imagination, it's overrated.
Okay. But have you considered the possibility, or do you consider it's even like remotely possible? Wormholes.
So those require matter that has some of the same awful properties that the matter required for the Alcubierre warp drive requires. And so I think it's not likely to happen. I think it'd be great if it did. If we could figure out a way to do that, I would devote my life to working on that. But I just don't see it as a opportunity.
What about teleportation?
Teleportation. So you mean like on Star Trek, beam me up?
Mm-hmm.
Yeah, I don't know. I can't even imagine how that would work.
Like you have to encode every single one of your atoms to reorganize themselves the exact same way as when they...
The sheer volume of information
Yeah.
would be amazing. So you have, there's a lot of information in each cell in your body, and how many trillions of cells are there? There's a lot. So I don't think we could store that information, at least at present. But our storage capabilities are going up exponentially still. And so maybe that's something that could happen in the future. They could break you down slice by slice and then reconstruct. You have to be really confident that they could do the reconstruction. That growth in storage capability that technology has been really important for Event Horizon Telescope, actually, because there's a lot of data involved in one of these campaigns. It's multiple petabytes of data. So about 5 petabytes for the 2017 campaign.
For 4 nights.
Yeah. So basically, you record a high cadence version of the voltage stream at each telescope, and then you cross correlate those. So you're recording this at I've forgotten what it is, 32 gigahertz or something like that. So you're digitizing it. And so if you tried to do this in sort of 2005, the required storage capacity would have been just ridiculously expensive, and it's still a big part of the budget of the experiment.
Thank you so much for coming and talking to us and teaching us everything you've learned.
Well, thank you for having me, Juan David and Ariman. It's been really great. Interesting to talk to you guys, and I wish you the best with your careers in engineering and with their talk show for the rest of the year.